So we have seen how maximization works for functions with only one variable. However, in reality, it's often the case that our model of interest has several variables. So in such cases, we will have to consider all the partial derivatives. What is that? So the partial derivative is the derivative of the function with respect to one variable. For example, with respect to x1, while keeping all other variables constant. And this is often denoted as the curve d of y over the curve d of x1, or just simply the f1.
Okay. Now are the examples of partial derivatives. The first example, we have y, which is a function of x1 and x2, which is ax1 square plus bx1 x2 plus cx2 square. So ABCs are constant, right? Now the partial derivative of y, I use the curved d here because now the function of several variables. With respect to x1, the partial derivative of y with respect to x1 would be the first term, a constant, rewrite. Power goes in front, right? So 2a x1 plus b is constant, x2 now treat it also a constant, so you write it x2 and x1 is gone, right? After taking the derivative. Here cx2 square, there's no x1 involved in here, so it's a constant in this partial derivative, and the derivative is 0. Move to the partial derivative of it with respect to x2. Similarly, now the first term we don't have x2, so it's constant and the derivative is 0, plus b again, now x1, and plus 2 in front, c x2. Second example, we have y equal to fx1 x2, which is e to the power of ax1 plus bx2. Now this is a bit tricky. It would be better for us to see how we treat some part of the function as constant when we rewrite it in a way that equal e to the power of ax1 times another e to the power of bx2, right? Factor out the exponential. So now the partial derivative of y with respect to x1 would be, when we talk about x1, this with respect to x2, this part of x2 will be treated constant. So we can just rewrite it times a constant, e to the power of bx2, b, e, times. Now, this is the exponential function, so that its derivative would be itself. However, x1 is another function, so function in function. So we must have the derivative of the inner function, which is a. Similarly, for x2, we have rewrite e to the power of ax1 the derivative of e to the power of bx2 is itself, and then the inner derivative, which is, in this case is b. Third example, we have another function which is a times natural log of x1 plus b times natural log of x2 as 1. The partial derivative of y with respect to x1 would be, there's a constant times, so we write it times, a times. The natural log of x1 is derivative is just 1 over x1, right? And then this part, no x1 involved, so it's a constant and the derivative is 0. With simply equal a over x1, right? And then again we have the derivative of y with respect to x2. Similarly, the first term gone away because it's constant now. B times 1 over x2, which is b over x2. Done. So now let's move on to the second order partial derivative. Here from the previous example we have that before I wrote down here. We have a function y of two variables, ax1 squared plus bx1 or x2 and plus cx2 squared. Okay, and we already taken the first partial derivative of the function with respect to x variables, x1 and x2. So now how to do the second partial derivative? By the way, I denoted f1 as the first partial derivative with respect to x1 and similar for f2, just to make it shorter in the way they call it. So we could also, for the second order derivative, we can take f11, which is the derivative of f1 with respect to x1 again. So this, and with respect to x1 here we have 2a, right? And then for f2 we could also take again with respect to x2. So it's actually f2, the derivative f2 with respect to x2, which is in this case 2c. And this, when you differentiate the function twice with respect to the same variables, it's called own second partial derivative, own. And then we also have crossed second partial derivative, which at the second route you take the derivative of the first one, the first derivative with respect to the other variables. So in this case x2, and here we have b. We could do the same for the other way by taking or by differentiate f2 but with respect to x1, and that is b, also b. So right here we could write an equal sign. And this is actually not a specific result, but it's a general result. So one way to describe the first and the second partial, only the second partial derivative, but the cross and the whole derivative. To put it on something, a matrix. So here we have a matrix. This is the first differentiation, and this is the second. Sorry. So x1, x2, x1, x2. Okay, so if the first route we take that we differentiated with respect to x1 and then again x1, that is f11, which is 2a. But if in the second route we take the derivative with respect to x2, then that means f12, which is b. Similarly, here differentiate twice with respect to x2, sorry. So that means f22 equal to 2c, right? And here f21 equal to 1, 2, 1, also b. So this matrix is called Hessian matrix, of second partial derivative, and it's symmetric by Young theorem. So Young's theorem say that the order of differentiation doesn't matter whether you first take the derivative with respect to x1 or x2. Sorry, this is the first route. But then when you turn to the cross derivative in the second route, the result will be the same. So f12 equal f21. And that's what's said by Young's theorem. And it's held for almost every function, which can be differentiated.
Because now we have more variables than before, we have to take care of more directions than before. Remember, when we have one variable only, we have two directions, either to left or right, but now it can move in many more directions. And because of that, for a point to be a local maximum, it has to be the case that no small movement in any of these directions can increase the value of a function. And the necessary condition for that is, at this point, all the partial derivatives of the function with respect to each single variables must be 0. So to put that into interpretation, that means that any input to the function must be increased up to the point that the contribution, the marginal contribution of it to the function is 0 already. And like before, we also have the second order condition to guarantee that it's a maximum and not minimum. So in this case, suppose we have two variables. The second order partial derivatives of these two variables has to meet this condition. The first two conditions pretty similar to before. You have the second order own derivative of each variable has to be negative. The second thing, this is the new thing compared to before. The product of the two own derivative, second order, minus the square of the cross derivative must be larger than 0. Why do we need this special condition? Because we want to avoid the case where the cross effect, summarized in f(1,2), the cross derivative, is going in the opposite direction of the own effect, and its magnitude is so large that it can offset the own effect.
Now let's try level up ourselves with an example of maximization for functions of several variables. We have a function y which is minus 2x, x1 squared plus 2x1 minus x2 squared plus 4x2 plus 5. First order condition. The partial derivative of y with respect to x1 must be minus 2x1 plus 2 equal to 0. And here we can already solve directly for x1, which is 1. Same for x2. So we have minus 2x2 plus 4 equal to 0, meaning x2 equal 2. Right? Are we done? No, right? We have the second order condition also, which we should check, at least for now. So the second order condition for this, we have to calculate the second O and cross derivative. So we have, let's take the cross derivative first. So dy with respect to x1 first, sorry, and then again with x2. So that means this one, right? And then we take the derivative with x2, but there's no x2 over here, so it should be 0. And now this the second own derivative. First with respect to x1, which is this term, and the derivative of this is minus 2, right? Similarly, we have the other second own derivative, but with respect to, sorry, dangerous mistake, x2, which in this case also equal to 2, minus 2. So put everything together, we have f11 times f22. Let me put it here so that doesn't confuse you. f22, and this is f12 minus f12 square, which is f11 is minus 2 here, times another minus 2 minus 0, which is 4, and that means positive. So the second order condition met, and this is a local maximum. Done?